I'm Jeremy Keene. I'm a senior researcher in the Distribution Edge Group in the Grid Planning Analysis Center, and I have led development of CADET over the past 2 years and continue to lead it on several projects that are using CADET. Privileged to work with the CADET team that you see in the lower right-hand corner. And if you have any questions or just want to shoot us an email, you can reach out to us at the email address cadet@nlr.gov. We'll also be putting a Microsoft kind of form in the chat that you can fill out with your email address and any questions you have, and we'll sort of send updates to anybody that's on that mailing list that we create from that. So I have a few goals for this webinar today. First, I want to share a few examples of distribution planning challenges that are especially difficult to tackle using existing planning workflows today. And then I want to set the stage for CADET. I'll introduce kind of what it is, our motivation for creating it, our design philosophy, and a few examples of recent uses. But just to get started, let's talk a little bit about the state of distribution planning today. Anybody tuning into this webinar probably knows that there are a lot of challenges that we face in distribution planning. I've shown a few bullets on the right-hand side of this slide. Many of you have probably heard about data centers or large loads that are driving large investments. And these create challenges around whether we're investing in distribution infrastructure at the right time to support the ramp up of these new loads, or whether we might invest too early and lead to stranded assets. We also have increasing intensity of storms and other natural hazards, which can lead to challenging decisions about whether we want to invest proactively or reactively. And we're trying to tackle a lot of these challenges essentially with one hand tied behind our back. A lot of the most skilled workforce is in the process of retiring, and we also have increasing costs and aging infrastructure that can make all of these challenges even harder. So one of the kind of key goals that I want to get across, whether you want to use CADET in the future or not, is that we can use modeling tools to help provide decision support to utility planning engineers that are trying to tackle a lot of these challenges today. Let me talk about a few more specific challenges that utilities are facing today. I've listed some of them on the left-hand side of this slide, and I'll tie them together with an example. Suppose you're a utility. Suppose you have 4 kV networks. These are older networks. A lot of distribution networks today are either 12 kV voltage class or 20 kV voltage class, and they tend to be poorly suited to host large loads or distributed energy resources. A lot of utilities are looking to replace them, but the replacement cost can be astronomical. We're talking about possibly billion-dollar rate cases. And so if you're a utility looking to make these replacements, you might think of other value streams associated with updating these 4 kV networks. You might think that they have value in the improved reliability or improved resilience. But in working through that problem, you might run into even other problems. It can be difficult sometimes to procure new transformers or conductors or other grid equipment. One option there would be to use non-wire alternatives, or what is sometimes called bridge-to-wires alternatives, where you use batteries and other distributed energy resources to provide capacity until you're able to procure the equipment that you need. This can lead to new challenges. It can be challenging to manage and to control all of those distributed energy resources. So there you might be thinking about a distributed energy resource management system for managing the DER and avoiding the costs and using the DER in the most effective way. So I'm just trying to kind of weave a picture of the challenges that distribution planners are faced today. We can't solve all of that at once, but I want to highlight that there's some sort of common aspects to these challenges. There's questions about the size or capacity of equipment that we want to procure, the timing, when do we want to get it, where do we want to put it? And there's a lot of dependencies associated with these different grid investments too. Like if you invest in a voltage class upgrade, that enables some things. If you invest in a distributed energy resource management system, that enables other things. So it's not a once and done decision that utility engineers are making. They need to think about the sort of long-term investment strategy, and there's a lot of different pathways that they can take in developing these strategies. So all of the different use cases then have some common modeling needs that are shown on this slide. For example, it can be very helpful to have a long-term grid investment optimization tool. It can be helpful if that tool provides multi-objective decision-making capabilities. So not just in considering what's least cost and most reliable, but also considering diversified energy and resilience and affordability. We talked about resilience on the previous slide. It can be helpful if these decision-making tools provide risk-informed decision-making. Customers are becoming increasingly vocal. They want to be part of the planning process. Often existing planning processes are not suited for that type of scrutiny. So any way that we can help make these processes more transparent or defendable and repeatable is useful. All of these types of analysis, they often require data being exchanged by many different utility planning departments, and therefore require a more seamless exchange of data analyses between load forecast, planning departments, operations, asset management, and others. And then finally, on data governance, I'll speak to this a little bit later too, but anything we can do to reduce data requirements and facilitate ingestion and conversion is really critical for the success of any modeling capabilities we develop. Now, I feel pretty strongly that all of this is possible. I feel that way because, in a sense, we're already doing it as an industry, but we're doing it in our bulk grid planning instead. And so we can draw inspiration from many aspects of bulk grid planning, where capacity expansion tools are used to suggest grid upgrades. Now, the focus of this planning capability is more on sizing generators, whereas in this webinar and with CADET, we're focused on trying to provide distribution capacity, our transformers and conductors and so forth. There's a lot of analogies still. And this process in bulk grid planning is something that we can kind of look to. We can see that it often provides a common tool framework for facilitating conversations between grid planners and the public, where in some cases there's distrust amongst each other. And it does that by not focusing on the outcome, say whether we want EVs or we don't want EVs, but rather on the modeling inputs and assumptions. So, instead of whether EVs improve affordability or not, we can focus on, okay, what are the right kind of EV load profiles that go into our modeling toolkit? The last thing I'll say is these capabilities, they're really about helping compare different upgrades. And the challenge here is that different upgrades have different types of risks. In bulk grid planning, one of the nice things about it is it's better defined in bulk grid planning than we currently define in distribution planning. We have, for example, criteria that we only allow 1 in 10-year losses of loads, and this enables comparisons of technologies, for example, between variable generation and non-variable generation on a level playing field. This is not the case in distribution planning yet, and it's something we need to keep in mind as we're developing these tools. Okay, so what is CADET? It stands for Capacity Expansion for Distribution Networks. And in short, it's a library and a framework for creating distribution capacity expansion planning tools. I should note there are several different domains within distribution planning. What we're really focused on here is how to create tools to help with feeder upgrades, or new transformers, or substations, or how to use non-wire alternatives. Just like some of the examples I gave before around voltage class upgrades, or implementing DERMS, or resilience investments, and more. Challenge with all of this is these are all very expensive, and there's a lot of uncertainty, and so it's really critical to be as systematic as possible. Another way to say that is we want to have repeatable and defendable and, whenever possible, transparent decision-making processes. One way to do that is to follow the processes that distribution utility planners are already following. They're defining objectives, identifying scenarios of interest, performing load forecasts and identifying system needs and solutions for those needs. So our vision for CADET is a tool that simplifies existing planning practices, enables integrated distribution planning processes, but is also aligned with this kind of standard workflow that utilities often follow. Let me describe a little bit more what we're doing with a very simple example. This is about the simplest example I could create for a distribution capacity expansion planning problem. Essentially, what we're trying to do is simulate the distribution planning process and to do it over long time horizons and to recommend high quality strategies for providing capacity. And so in this cartoon that I'm showing on the right-hand side, we have a very simple distribution network with a few loads, and we're forecasting ahead, and we're seeing that we're going to start running into constraints. So first we see there's a transformer that's becoming overloaded. And then looking further into the future, we see a new customer coming online, and that's causing further overloads. And there's immediate questions about the timing of our investments. Do we want to immediately replace that transformer when it happens, or knowing that this new customer might come online, do we want to replace the whole feeder and achieve economies of scale? Or should we strategically place distributed energy resources and try to avoid all of those investments altogether? Now, this is a very simple use case. There are many, many potential use cases for distribution capacity planning tools. And this has really led to our design philosophy for CADET. So there's many use cases. There's hundreds of journal articles on distribution capacity planning. But the reality is these methods are rarely adopted. So methods exist for helping with reliability planning or substation design or low voltage network design, or helping to identify solutions for problems with multiple objectives. We're planning with DER. The problem is typically these methods are kind of proof of concept. The code is rarely available. It's not often extensible to other problems. You might solve one very particular problem for one use case, but modifying that one tool to be applied to another would be expensive. And so the approach that we've taken with CADET is having a flexible tool with more of a building block architecture that can be applied relatively quickly to different use cases. Now, it's relatively quickly, that's relative, right? So we're talking about, months or a year sometimes to turn around different tools depending on the use case. But let me kind of explain why this is important. Regardless of your use case, you're going to need to simulate the flow of power through distribution lines and transformers. That's going to be based on a forecast, and that's going to tell you what kind of upgrades you might need to make. But different use cases have very different needs for the fidelity of that modeling, that flow of power through your lines. For example, if you are trying to do a study that's statewide or nationwide, you probably want to have a fairly simple representation of your distribution network. You could have it as simple as only a substation and kind of feeder level constraints. Now, this is low fidelity. You won't capture voltage violations on your network, but it scales to that statewide or nationwide scale. And importantly, it has lower data requirements, which is really critical since data is in, we'll say, a very heterogeneous state within the industry. Alternatively, if you're especially focused on a use case where understanding voltage violations is important, and you're looking at a much smaller scale, like a feeder or just one substation, it might be appropriate to have a higher fidelity modeling approach with, and you can handle those high data requirements and you're not worried about scale. So what we've built into CADET is sort of the option to sort of move between these different representations depending on the use case that is the scale there, the fidelity that's most appropriate for your use case. Here's an example of a distribution model. It's got 20,000 nodes. 58 megawatts of power. But it might be that there's a lot of data challenges on some of those laterals or secondaries, and the questions that you have don't really need that high of a fidelity. So here's another version of that model that's gone through one of our network reduction processes where we turn it into a three-phase model, which in reality is often aligned with the needs of the utilities that we're working with, this simpler representation. So with CADET, we're trying to sort of provide these capabilities to different researchers or utilities that are creating these tools, so they don't have to reinvent the wheel. You might be a researcher, you might be thinking, well, I can do network reduction as well, but a lot of people can do network reduction. Let's stop reinventing the wheel. Let's put it in a common library so that we can move on to more interesting aspects of the tool development. So the way we're doing that is kind of having an ecosystem of capabilities. So in integrated distribution planning, we often talk about things like data governance, best practices. This includes things like data standards and data reconciliation between various sources. Another way to put this is, the first challenge of developing any tools or doing any kind of analysis is simply compiling data from a lot of different heterogeneous sources and putting it into a common format. It's a pain and it can take a lot of time. So to ease this, at NLR, we developed what we call grid data models. It's an open source data model, an internal data model we use. That is the data model for CADET and other NLR distribution modeling tools that you can see on the slide here. One really important feature of grid data models is that we have a lot of validation consistency checks. So once the model is built, various checks are run to make sure it simply makes sense as a model. An example of that would be a transformer with a nominal 12 kV voltage being attached to a bus with a 23 kV voltage. That just doesn't make sense. GDM, as we call it, would flag that and sort of notify the user that it needs to be fixed. By taking this approach, we've really saved countless hours in troubleshooting our models. If you've already used Ditto, that's a conversion tool that we have had for many years here at NLR, and it helps convert things, distribution power flow models from, say, SIME or Synergy or SIM to, say, OpenDSS. Now GDM kind of sits as the internal data model for Ditto. So if you're using Ditto, you're also using GDM. If you're using ERAD, ERAD is a tool that simulates the impact of natural hazards on distribution systems. To use ERAD, you need to use GDM. The idea is that we have one data model that works for all of these tools. So once you can work with one tool, you can work with all of them. And it's a first step towards using CADET because CADET uses GDM as well. So I want to kind of talk through how you might build a tool in CADET. In this case, I'll use kind of a simple example of how we would build a tool that gives upgrade strategies to accommodate new loads. And if you're thinking, okay, at this point, why do I want to use CADET? Maybe you're a researcher and you're interested in developing distribution capacity expansion tools, but you're content using Pyomo or CVX-Pi. This is really the slide for you where I'm going to kind of point out some of the features, modular capabilities that we have part of our library that can, in my opinion, make your life easier and let you focus on the sort of more interesting aspects of optimization. But let's first think about just some of the basic things that we'll need. We need a distribution model. We need upgrade costs associated with different equipment. We might need time series data if we're doing more than peak load snapshots. And we'll need to consider what are the constraints that drive investments. Certainly there's going to be budget constraints, but there are also operational thermal limits and voltage limits. thermal limits could be that you replace a transformer when it's at 80% of its loading, or 100% of its loading, or maybe 120% of its loading for 4 hours, right? There's a lot of ways to define this. And that sort of speaks to the need to keep this flexible. After that, we have to recognize that distribution models are big, right? They have thousands of assets. They have tens of thousands of parameters associated with those assets, and we need some way to manage all of those parameters when we're building tools. And we need methods to identify good upgrades from a large set of possibilities. And then finally, once you identify what good upgrades are, you need to kind of figure out a way to get those solutions back into a working power flow model. And what I'm showing here is kind of an example workflow of how you could use Cadet. Again, it's designed in a modular way, so it doesn't have to be like this. But we could imagine for creating this new tool for accommodating new large customer loads, we use NLR's Chronify tool, which helps map time series data to a common format. Maybe you want to test your tool on a common use case. You can use our GDM loader, which is an open source tool that comes along with GDM to load in a test case power flow model. And I'll get to this in the next slide, but we've also created a cost database for costs of different kinds of equipment. And these three things, they flow into a power flow model and a GDM catalog, or you could think of it as an equipment library, essentially a set of equipment and their upgrade costs that you could consider when you're thinking about your investment strategy. Now, again, all of this is still a lot of data, and we need to parse that data into sort of the key pieces of information that will go into our optimization tool. And that's what managers are for. These are just SQL-like databases for efficiently storing and retrieving information that are used to build our tool. The challenge is that when you're developing optimization tools, there's so many thousands of assets and thousands of parameters. Just building these tools themselves can take hours. And so making sure that we have efficient processes for, again, retrieving that information and using it to build variables and constraints and objective functions in our optimization tool is really critical. Now, in our Cadet opt library, we're also trying to avoid the reinvention of the wheel here, right? So there's a lot of people in the distribution planning space that have created linearized power flow equations. But our philosophy is let's not have everybody redo that every time they want to make a new optimization tool. So that is an equation that's included in our library of constraints, and many, many others that can be reused and modified for whatever kind of tool and use case is being developed. So once that tool is developed, you can run it. Cadet interfaces with Pyomo, and we have some early interface built in with CVXPy as well. In theory, it can work with sort of any optimization tool like that, and those can then be used to use solvers like Express or Gurobi or Highs. Suppose you go all through all of that and you get a solution. The sort of final step here is you need to convert that solution to a working power flow model. Now, you might have gotten a solution in this particular tool that says the right answer is a battery that is 0.9743 megawatts, right? I'm being intentionally ridiculous with the significant figures because we all know in this case, a battery of that precise size doesn't exist. So one common workflow that is often required is that we need to take an optimization result and then we need to map it back to a standard size that exists in the real world. And so this mod.sys block that you're seeing in the lower left-hand corner is the sort of piece of Cadet opt that allows that to be done. Again, the nuts and bolts of running optimization problems so that optimization developers can focus on sort of more interesting aspects of the problem. Now, speaking of a pain point that's been part of distribution modeling for years, it has been always very challenging to get realistic distribution costs. You might have used NLR's distribution unit cost database in the past. I believe that's still up on our website. It's a spreadsheet that we used particularly for hosting capacity and interconnection analysis. This is not the same thing here. We've done a complete overhaul, and I don't know if it's been released just yet, but will be released in the coming weeks. Yeah, it includes equipment, transport, and installation costs. It's sourced from thousands of manufacturer specification sheets and labor manuals. And one of the especially exciting things about it is it comes with automatic updating routines. So we're scraping a lot of these websites and documents, and then automatically updating them with new information as it appears, or removing if it's no longer there. So this can be used for all kinds of distribution plan analysis, but is especially helpful for distribution capacity planning. Okay, so I've described a little bit about the workflow of CADET and how in theory it can be used to create distribution capacity planning tools. But you might be wondering, well, does it work? Have you actually used this framework and library to create your own tools? And it does. Now it's a relatively new NLR tool, I should say. We started development 2 years ago because we felt it would have a lot of value for distribution engineers. But we've already seen a lot of demand in terms of potential projects. And this slide shows different tools that we have developed or are in the process of developing with CADET. I'll also note we are at a stage right now where we are looking for beta testers to use CADET. And after we kind of go through that process, we do hope to open source the library. It's not open source yet, but very much interested in having these early beta testers. So I want to start. I'm going to go through all of these tools, some more briefly than others. But I want to start by talking about one particular tool that's been especially successful, and that is our integrated T&D capacity expansion capability, or at least the CADET side of it that we think enables T&D capacity expansion. So non-wire alternatives, they have distribution benefits, but they also have generation and transmission benefits. And the question is, how do we consider these benefits and constraints and value streams for distribution-sided non-wire alternatives? Before I really get to the answer to that, I'm going to start with a basic, but this time real, example of a use case with CADET. So here I'm showing a test case that we have available for people to use through the GDM loader. That's a 5 MVA, 12.47 kVA substation, 3 feeders. And on the right-hand side, you can see the loading on different transformers. And this is sort of the exponential loading that's happening. There's also new customer loads that are pushing these transformers further into the red, meaning that they're way, way, way overloaded. These color boxes on the left are also showing the year in which different transformers and lines are exceeding their capacity. So what we're going to do is it's overly somewhat simplistic comparison of traditional wires and non-wire alternatives. In this case, we'll be looking at batteries. So in this plot, what I'm showing is the optimal investments over a 20-year planning horizon with and without the option to use batteries. So again, this is years on the horizontal axis, and this is overnight cost, so the cost of the battery if you were to pay for it all today. And then for each year, I'm showing 2 columns. One of those columns is essentially the investment strategy if you don't have batteries in the picture. And then the column on the right for each year is showing the investment strategy if you do have batteries in the picture. And by doing this, we're able to see some things that are of interest in distribution planning today. like the ability to right-size assets or defer others, defer asset investments to later years. So for example, in the year 2025, without any batteries, there was about $100,000 of cost in transformer upgrades and reconductors. But if batteries are an option, then batteries would be placed there instead. And we can see that as probably a deferral because we see other years where there's more investment in conductors and transformers, even with the batteries. Furthermore, we see some years where there's just a reduction in the amount of investment in transformers and conductors when you have batteries relative to when you don't. So I see this as an example of right sizing. As an aside, when I say right sizing, I mean installing a new conductor, transformer, or other assets. So that's not too big and costly, right? But just big enough to meet the load demand over its lifetime. So in this case, the possibility that we can use batteries at a later point means that maybe we can size the conductors and transformers smaller earlier on. Now, the results of this are shown on the right-hand side in terms of the total net present cost. This is essentially a time value of money type calculation that we're doing. Without any batteries, the net present cost is around $660,000 and comes down to $620,000 with the batteries. Then you might ask, you might see that I've listed some unit costs, and these are kind of average unit costs for the transformers, conductors, and in this case, a 4-hour battery that we used. And you might be wondering, well, why is it that we would have used these batteries at all, given that on a per kW basis, they are significantly more expensive than transformers and conductors. And part of the answer to that is on the next slide, but I'm going to explain that with something entirely different. I'm going to explain that with potatoes. So yeah, why use DER when it's more expensive? The answer of that, you can think of it like buying potatoes in bulk, right? You can buy them in bulk on the market. You can get a great deal on a per unit basis for all of those potatoes. But if you're buying a warehouse of potatoes, you've got financing costs, you've got maintenance costs to avoid spoilage, so it's a much larger investment. Buying a warehouse of potatoes, you could think of that as buying a really large substation or power transformer, which often come in set sizes so that utilities can standardize them, and we kind of, as a result, require a much larger investment. Alternatively, you could buy the potatoes in smaller quantities when you need them, right? They're going to be more expensive per potato, but the ability to buy what you need, or in this case, buy maybe a battery or distributed energy resource when you need it, even if it's a higher unit cost, might allow you to reduce the overall planning costs that you have. Optimization is a great way to kind of reveal these kind of effects. Sometimes you get results that are hard to explain, and then it forces you to kind of dig into some of these nuances of planning. So I said we were going to talk about integrated T&D planning. So what does all of this have to do with integrated T&D planning? I'm going to explain that in this slide and the next one. As we just saw, battery energy storage can potentially reduce long-term planning costs. And a challenge of really doing that calculation correctly with non-wire alternatives is they might not accurately capture the value of DER for the bulk grid. So over the past year or so, I've been working with my colleague, Brian Palmentier, and we've been developing the concept of distribution cost curves. Essentially, these are taking what I just showed you on the previous slides and doing a sensitivity analysis where we have an additional constraint on how much DER we're considering at every point along this graph. So we rerun our capacity expansion tool with 0 DER or with 1 megawatt of DER or maybe 20 megawatts of DER. And we see how those different amounts of DER lead to total overall distribution costs. Now, when this green line, which represents our distribution cost and the cost of the in this case, front of the meter DER, is below this dashed gray line, we're in a region where the DER are helping us to reduce our costs relative to a strategy with only traditional solutions. Once it gets into the blue region, and especially the red region, now we're exceeding the costs that we would have had without any distributed energy resources. So could it still be a good option to install DER when you're in the purple to red region? The answer is maybe, right? Because new generation and transmission lines are also challenging to build. And the additional costs of the non-wired alternatives, or the DER, that are reflected here may actually be justified when you look at the larger picture of options and costs that generation and transmission planners are considering. The other valuable thing about this approach, there are a lot of modeling approaches to do this, I should say, but one particularly nice thing about this is it fits well with existing bulk grid capacity expansion tools that often use mixed integer linear programming. So the idea is that we could create these distribution cost curves for a given substation or maybe a service utility service area, and pass these cost curves to our distribution capacity expansion modeling tools, and they can run with it there to see if the DER are cost effective or not. And we're working with a couple utilities on this right now. Here's an example of what those cost curves look like for in this case, it's a synthetic distribution model. The yellow line is showing the distribution cost curve and all the T&D costs and benefits of DER. It can also be useful to break down constituent costs. So this particular cost is showing the DER costs by themselves and the avoided energy and demand cost and the distribution upgrade costs for this particular problem. So moving on to some of our other tools, I'd like to next talk about how we've used CADET to help with something totally different, resilience planning in Minnesota. Here we worked with Iowa and a couple utility co-ops, and we're less concerned about long-term loading capacity and more concerned about withstanding natural hazards. In this case, we're concerned about flooding. So we used our ERAD tool, which, as I mentioned before, helps simulate natural hazards and the intersection of those hazards with distribution equipment. And we use that to determine how different floods and probabilities of those floods sort of intersect with different distribution equipment. That feeds then into CADET using our common GDM model to prioritize investments by looking at the probability of different flooding scenarios, their impact on lost customer load, and the cost of those different hardening measures. In this case, we looked at pole hardening, substation walls, and we looked at undergrounding. One kind of cool thing about this was it gave us a chance to test out the use of stochastic programming in the CADET optimization framework. Stochastic programming essentially allows you to optimize investment strategies considering that there's uncertainty in a lot of the inputs. In this case, it's the uncertainty of flooding. But it can be used for a lot of other use cases that we hope to apply it to in the future. For example, what's the best way to plan when you have a lot of uncertain load growth or uncertain data centers that may or may not come online? What's maybe a least regret strategy that you can move forward with given that uncertainty? Stochastic programming can help with that. Another capability that we're in the process of developing, really just starting on this one, is a tool to help plan for EV charging stations. So this slide shows an early prototype of our user interface there. The target audience in this case is utilities, regulators, and researchers. And the basic idea is that a user can input some kind of charging station capacity and where charging stations might go, and CADET can help identify, if you have that flexibility for where to put them, the best locations for where they could go, the best meaning the least cost. So this would tell you the investment strategy of the charging stations and various grid equipment to host those charging stations. It can also plan to kind of tell you how managed charging might help reduce those investment costs. And another kind of common problem with this kind of thing is when developers are trying to build charging stations or DER or anything that might trigger an upgrade. A challenge in making those happen is the first person to trigger an upgrade is often responsible for the cost of it. And one of the reasons we do that is we don't have a great sense for how those investments might be triggered in the future by baseline load growth. So one of the nice things about Cadet is it can forecast that load growth out into the future. It can look at a business as usual scenario without the charging stations and see what kind of upgrades would happen anyway, and then give you an idea of the incremental costs associated with the charging station, and then more fairly allocate costs among developers and customers. This tool is a work in progress. We're just starting it, like I said, so would be particularly interested in hearing from anybody sort of interested in this capability. Last, I'm going to discuss the concept of distribution system adequacy, which was inspired by work we've done with utilities and their feedback, and kind of goes back to one of the key points I mentioned at the very beginning of this presentation on trying to include risk in our distribution planning processes. So a couple of years ago, we wrote a white paper on distribution capacity expansion current practices. You can find the link and title down in the left-hand corner there. And there is a lot of sort of interesting sort of findings coming out of that paper. But one that's relevant here is that PEPCO, who is a co-author on this white paper and serves Washington, D.C., observed correctly that we often have metrics to align our business planning with business objectives, right? An example of that is SAIDI and SAFE and utilities tracking those scores very carefully. And then going on to point out that what we don't have is a set of analogous, holistic, technology agnostic metrics that would level the playing field for fair comparisons for traditional solutions and non-wire alternatives. So this has been something we've been working on in a couple of ways. We've been working, for example, with Lawrence Berkeley National Lab and defining a way to do these fair comparisons using the concept of what we call distribution system adequacy, which is analogous to resource adequacy. And we're looking to define metrics like effective load carrying capability that are used on the bulk grid that kind of help us compare, again, variable generation with non-variable generation. So why is this important? So as it stands today, risk isn't defined very well in distribution planning. It's not, like I said before, we don't have a 1 in 10 year loss of load criteria that we have on the bulk grid planning. And so there's a sort of a need to develop those foundational framework. And that could help with really practical challenges that we have today. So if you look at the distribution network on the left-hand side, you see there's this overloaded area on the substation on the top left. And I'm just giving two perspectives of a planning engineer and a DER developer. A planning engineer might be thinking, would I use DER? Is it going to be available when it's needed? On the other hand, and they might be right in some respects. DER in some respects is not as dependable as steel in the ground, transformers, and conductors. The DER developer, on the other hand, might be saying, well, hey, the grid goes down from blackouts and from storms and all kinds of things. And DER could potentially be available when the grid is down. So both our planning engineer and our DER developer are pointing out different elements of risks associated with our different solutions. And what we hope to address is a way to capture all of those types of risk for that level playing comparison. There's some planning basics that need to be included and that are included in the CADET sort of framework. An example of that would be utilities using switches to transfer load between feeders and to stay within their capacity limits. So my simple cartoon shows power being transferred back and forth between this overly simplistic substation. And distribution networks are typically designed to have enough capacity during these kind of contingencies. Obviously, this is a cartoon, but when you have a real distribution network, this becomes a lot more challenging. It becomes even more challenging to do this analysis with contingencies, and it becomes further challenging still to do it when you're considering the use of DERs, like in this example where we have a battery that might be situated somewhere between both substations and adds another factor for consideration for that contingency analysis. It's possible that that DER could cause hosting capacity violations during a contingency, or it's possible that because of where that DER, this battery is situated, it's able to provide capacity to the different substations during different contingencies in a way that makes the grid actually more reliable. And so these are basic modeling capabilities that we feel are necessary to be able to do the kinds of upgrade comparisons that utilities need to do. And we're using them. We're using them in Pittsburgh to compare traditional upgrades with combinations of batteries and building upgrades. And the last thing I'll say is, like if you're joining us from a utility and you're doing N-1 contingency analysis, but you're not including distributed energy resources in that contingency analysis, you're not alone. This is something I've heard from other contingencies or heard from other utilities, and it's a challenging thing to do and an example of how distribution planning decision support tools like we create with CADET can really reduce the burden on distribution planners while allowing us to meet the kind of planning and design standards that we expect. And that was my last slide. So we'll move on to any questions that folks might have.
Wonderful. Thank you so much for the presentation. We have a few questions that we can go through, and then I'll let you know when we just have a minute left to wrap up. So first question is, how easy or difficult is this model to use for a company with no modeling expert on staff? And part two is your model applicable only to the USA?
Yeah, that's a good question. So there's sort of two types of users one could imagine for CADET. As I've mentioned throughout this presentation, CADET is it's a tool for creating distribution capacity expansion tools. It's a framework and a library that allows different tailored tools for different use cases because there are so many of them. We didn't want to just create one and then not be able to address other needs that utilities might have. So if you don't have any modeling experience, your probably best approach would be maybe to reach out to myself and tell us about your use case, and we could see if there's an existing CADET tool that might be sufficient for your modeling needs. But if you don't have that modeling experience, you're probably not going to want to use the CADET framework itself. You would want to use one of the CADET tools that are created. As far as whether it can be used outside of the US, yes, in general, the basic principles and capabilities that we've created in CADET can be used in the US or they can be used in other countries, with a caveat that there are certain designs that are more common in the US and more common in other countries that might create a little bit of extra work in creating the final CADET tool. An example of that would be the secondary networks in the United States tend to be split phase transformers and require certain modeling requirements, whereas in Europe they tend not to use split phase transformers, have different secondary networks that maybe our existing tools haven't fully or aren't as mature with.
Next, is CADET only useful for capacity planning, or can it help design other distribution optimization tools?
Yeah, I mean, it can It's a good question. It can be used to create other optimization tools for distribution networks. The sort of key capabilities of Cadet are the ability, like it has a library of constraints that are generally geared towards distribution capacity planning, but it also has certain capabilities, like I mentioned, ModSys and GDM and our data managers that are useful for any kind of distribution planning tool. And sort of a lot of those capabilities I could very much see being useful for, developing a new DERMS algorithm, right? That's less squarely in the planning space. So yeah, it could be.
These next two questions just came in, and I'm going to combine them because I think they're similar. It says, where does the data for the distribution model come from, the local utility, and how can a state agency use this tool for planning and policy recommendation without access to detailed distribution level data that utilities typically possess?
Data is a real challenge in this line of work. Your highest quality data is, of course, going to come from the utility itself, but there are data challenges even in that. We are developing different sort of methods for getting synthetic or reasonable distribution modeling representations, but we would need to maybe talk more about the specific use case that this questioner is interested in to know if those kind of synthetic modeling approaches are appropriate or not, right? So yeah, there are options in short, but it really depends on the specific use case.
This next one says, please describe how Cadet handles economic analysis of different investment strategies and the methods used to evaluate cost effectiveness of new substations, energy storage solutions, and customer energy efficiency programs.
Yeah, so the accuracy of all of those things will depend on the specific analysis you're doing. For example, if we're looking at batteries, we might here at NLR use our annual technology baseline, which has battery costs, and Cadet has the ability to include capital costs as well as O&M costs, as well as avoided costs for all of these different technologies. Ultimately, like if we're working with a utility, we would much prefer to kind of gather those costs, all of the costs that I just mentioned. We'd want to work closely with the utility to make sure that we're accurately reflecting the kind of costs that they're seeing, which are going to be maybe a little bit more accurate or relevant than what we can pull from catalogs and manufacturer specifications.
Great. This next one says, how do you handle the various types of network model software and debug issues within them to transfer to Cadet models and workflows, and then validate for confidence in the results?
Yeah, this is a huge problem. As I kind of mentioned throughout the presentation, there's just simply a huge number of assets and parameters associated with those assets, and bad data is just kind of rampant throughout most distribution models. So this is not a problem that has a silver bullet, but we are tackling it in a lot of different ways. So I mentioned grid data models, and one of the key features of grid data models is the fact that it runs validation. So we would use our Ditto tool, we would pull in a utility model into GDM, and if there are errors, we have all sorts of validation checks that are hopefully going to identify those, and then we can work with the utility or maybe just use common sense to correct those errors. And then that's on the sort of input side. On the output side, we often in Cadet use simplifications, like I mentioned. We do network reduction, or we might go from use a linearized power flow solver, and those can introduce sort of errors too, right? And so after running any Cadet tool, we have workflows in place that take those results that turn those results back into a power flow model and an AC power flow model, and we can sort of at least validate the result with the full network modeling and highest possible network fidelity.
Awesome. Depending on how long your answer is, this one might be our last one. The questions asks, what level of automation exists in Cadet? How much of it is operator/mouse driven, for example, for building the model and running many engineering scenario analyses?
So I would say not very much. Automation, if I'm understanding that correctly, was not the primary goal of Cadet. The primary goal of Cadet was having a kind of very flexible approach to creating different distribution capacity expansion planning tools. And so it's modular, right? Like there are different capabilities that are appropriate for different kinds of tools, but they really require somebody with Python experience or distribution modeling experience, optimization experience, and so forth. That's for Cadet, for our library and framework for creating capacity planning tools. Now, if there's a specific use case that you're interested in that relates to capacity planning, as I said, there are many use cases, right? But like if we knew what that use case was, perhaps an example would be EV managed charging, then we can create a user interface, and we're kind of in the process of that can be much more automated and use various techniques for making this simpler for a kind of a basic user that doesn't have the kind of experience that I mentioned before.